We will try to go back to Stuart Matthews.
So my task today is to give you a brief update on the work that we've been doing on Model Code 2020. I'm Stuart Matthews, I'm the convener, and my colleague Agnieszka Bija is the deputy convener. So let me move on rather than waste more time. Looking backwards, there are 4 previous codes, one from 1970, 78, 1990, and 2010 being the current code. And these codes have had an influence upon the development of Eurocode 2 and also upon the development of Asian and African model codes. But what we're moving on to now is, as you've heard, Model Code 2020, and this will be for the first time including comprehensive provisions for dealing with existing structures. But before we embark on that, I thought I'd just say a few words about what a model code is. It's a synthesis of international research and industry materials knowledge and expertise. So it's a pre-normative document, but it's an important step in the process of converting such knowledge into practical guidance for the design of new structures and also the life cycle management of existing ones. So what we're doing is bringing advanced knowledge to industry practitioners and making it available also for national and international code writers. So our goal with Model Code 2020 is to bring together coherent knowledge and experience for both design of new structures and the life cycle management of existing ones. So this involves improved structural design and assessment methodologies, the application of improved materials for new and existing structures, and we'll talk more about that as we go through, but importantly, adopting an integrated life cycle approach within the framework of sustainable development. But those are just a few headline points. And so I'll give some background on that, but I'll also seek to draw out to illustrate some aspects of the innovations in Model Code 2020. But again, these are quite selective and there are many other things I can't talk about today. So this presentation contains many additional hidden slides which I can't show because of time constraints, but will be useful if you wish to review, get more detail on many things that I talk about. So our starting position was Model Code 2010, and we're seeking to move across to 2020. 2010 was in 5 parts, 10 chapters and about 400 pages long. Model Code 2020 is in 9 parts. 35 chapters are envisaged. We don't know the page count at the moment, but it has a greatly extended length because of the vastly increased technical scope from technical developments, but also dealing with both new and existing structures, i.e. the portfolio of concrete structures which exist. There will be suites of FIB bulletins to provide additional supporting information which enables the authors of those areas to go into more technical detail, but also to help us reduce the page count of the main Model Code 2020 document. An important and significant aspect of the framework is sustainable design. It's becoming an increasingly important issue for us all. Clearly, we're looking to have an ability to design buildings and construct assets with low or perhaps no carbon impact. We're looking for improvements in the efficiency of material usage and structural forms, delivering such advances. We must conserve and reuse existing buildings and extend the useful life of assets where possible. And those activities require an understanding of old materials, existing materials in currently present concrete structures. We need to design for more realistic loads, so focusing upon the actual performance requirements. And also one of our objectives is to try and reduce barriers to the efficient use of materials. Durable concrete can be made with less than 100 kg of cement per cubic metre. And one of our other goals is the adoption of emerging intelligent technologies and getting feedback on the performance of structures through monitoring through life. Sustainability is an overarching framework within which Model Code 2020 is being built. You've heard a little bit about this from the preceding speaker, but we have the three pillars of sustainability: social, environmental performance, economic performance, but also there may be some special considerations in particular circumstances, such as a greater emphasis upon the resilience of the performance of the structure. So that gives us a series of performance requirements which enable us to select design and assessment parameters which guide our development of candidate design and execution solutions for new build, or candidate management intervention scenarios for existing or adaptive buildings. So that process will help us identify the most suitable scenarios, most suitable options for detailed examination, pretty similar to the way that conceptual design evolves possible alternatives for a design solution. We're linking to the UN Sustainable Development Goals, which is part of their 2030 Agenda for Sustainable Development. Model Code 2020 seeks to contribute to many of these objectives, and we see that there is the potential to contribute to 9 of these. So you can see these here with the blue surrounds. But in terms of conceptual scope for Model Code 2020, we're dealing with new structures, existing structures, but also the interaction between these in terms of adaptation, new structural members as parts of existing structures, retrofitting, and those types of activities. I'll just briefly touch upon the table of contents. Today, I'll only itemize the main parts of Model Code 2020. The presentation contains additional slides listing the 35 individual chapter headings, but I don't really have time to go into that today. So here we have the 9 parts. Those that are familiar with Model Code 2010 will recognize that the structure of the code is fundamentally the same as 2010. But of course, as I've mentioned, it's greatly extended because of the much larger technical scope and coverage, which includes existing structures. So if we look down the list, we have scope and terminology and basic principles in parts 1 and 2. A new part, 3, deals with actions on structures, such as probability distributions for probabilistic design and assessment. Parts 4 and 5 deal with input data for materials and interfaces, as the current code does. But of course, as we have more materials, as we're dealing with existing structures and new materials for new construction, we have A, more materials, and B, more interfaces between materials to deal with. The main content of the code is part 6, which deals with design and assessment procedures. So that's the essence of the technical content. Part 7 deals with execution, so that's the construction of new structures and interventions and adaptations upon existing structures. Part 8 is dealing with through life management, which in the current code comes under the title of conservation. And part 9 deals with dismantlement and reuse. So that reflects the requirements of the circular economy, which we are gradually moving to over time. In terms of the development of Model Code 2020, we've been working on this since 2016, and we're now in a position where we hope by the end of 2020 to have all the author drafts for the various sections which have been defined. We have some finished contributions already. Once we have all the author drafts available, we will go through a process of harmonizing those to produce a coherent whole coherent document. And we hope that that might be done by mid-2021 and perhaps in time for the FIB symposium in Lisbon. Obviously, this is an extremely challenging timescale for the magnitude of the task which is underway. And like everybody else, we've had impact from the COVID virus situation. Let me just touch upon some aspects of concrete materials. We've learnt over the years lessons from old structures, contemporary and recent structures, as well as from material studies. In Task Group 10.1, we've defined a whole series of action groups to complement the FIB commissions, which deal with areas of overlap or areas that FIB doesn't particularly cover in a coherent manner. So Action Group 13 deals with concrete models. That was formed last year. So what I'll just say about this is some of the lessons that we've learnt over the years and how that's guided perhaps approaches to changes in the code. The graphic on the left deals with compressive strength of concrete versus time. The development of strength over time is also affected not only by hydration, but also by loading effects. So an unloaded structure or a loaded structure can have a different in situ compressive strength. And you'll see from the graphic that a loaded structure may have 20% more compressive strength. If you look at the graphic on the right, carbonation depth versus time, you'll see again that highlights loaded and unloaded experience. So the behavior and the depth of carbonation is dependent upon the stress type and stress level. So loaded structure with more microcracking, the carbonation depth is likely to be appreciably more than in an unloaded structure. Continuing in this theme, on the left-hand graphic, you've got chloride diffusion coefficient on the vertical axis and time on the horizontal axis. But again, the influence of load history and past behavior of the structure is brought out by those curves indicating that chloride diffusion can be significantly higher in a highly stressed structure than in an unloaded structure. And if we turn attention to the right-hand graphic, which shows total shrinkage versus compressive strength, you'll see that there's a downward branch to this, which was our assumptions on the behavior of high-strength materials until about 1990. But experience of measuring test data and performance of actual structures suggests that that behavior is not correct and much higher shrinkages occur for these high strength materials that we're now dealing with. This slide deals with the ranges of model codes applicability, both in the past versions of the code and what we envisage for Model Code 2020. We have 4 columns: criterion, Model Code 1990, Model Code 2010, Model Code 2020. And you'll see, if you look between Model Code 2010 and Model Code 2020, that the strength ranges are similar. But with Model Code 2020, we're seeking to incorporate advances relating to green or eco concretes, the influence and behaviors of ultra-high performance concretes. Of course, dealing with existing structures, we need to deal with intervention materials for protection or repair, and also an ability to understand the behavior of old concrete to use this in assessment procedures. But we do recognize that high performance and coming materials with new binders will certainly relate significantly to understanding gained by test standards and recommendations. There's been a significant update of the equations and relationships for concrete between 2010 and what we're envisaging will be included in Model Code 2020, and the factors are listed here: tensile strength, fracture energy, multi-axial stress-strain relations, compressive strength with time, development of tensile strength and modulus of elasticity with time, the behaviour of concrete compressive strength under sustained loads, influence of shrinkage and creep, and particularly at high stress levels, concrete at elevated temperatures, fatigue behaviour and impact behaviour. So these relationships which were presented in Model Code 2010 are evolving. I again don't have time to show all of these, but I'll show one example in a second. We maintain concrete classification, so compressive strength and density as Model Code 2010, but we're envisaging introducing a classification on durability based upon resistance classes, based upon test results. So this is an example of what's changed in regard to tensile strength of normal weight concretes. In Model Code 2010, there were two relationships for concrete grades below C50 and concrete grades above C50. But if you look to the bottom in the left-hand column, you'll see that there's now one relationship which deals with all concrete grades. And on the right-hand side there is a graphic which shows a relationship between those two. But clearly having one relationship is more convenient and eases use of the model code. Just looking at the classification of concrete with respect to modelling, the proposed principles for Model Code 2020 with 3 rows: column type, model basis, and validity ranges for strength-based models. What we do differentiate is between what we term conventional concretes, so normal strength and high strength concretes, and what we're going to term non-conventional concretes, which I'll say a bit more about in a moment. In terms of the validity ranges based on upon strength based models, you can see these indicated in the 3rd row. But the point that we need to bring out is that these will have to be related to a concrete code, such as EN 206 or another concrete code, but the plans are for a development of a future FIB concrete code dealing with concrete as a material. Again, as I mentioned, non-conventional concretes, eco-concretes, ultra-high performance concretes, and so on, well, and existing old concretes will need to be largely based upon performance tests, which will have to be defined in Model Code 2020. So summarising, conventional concretes, such as the relationships I talked about previously, with that big long list, which you see in Model Code 2010, but will be revised for Model Code 2020, are applicable to what we're going to term conventional concretes. And for non-conventional concretes, i.e. the green box, we will use a lot more testing, because those conventional models will not be appropriate for those materials. So let me just move on to improved materials and mechanical models. One of the things that we're looking to do is to have better models for assessing the actual capacity of a structure. Model Code 2010 and 2020 were seeking to adopt performance-based design. So we need to assess the ability of the structure to fulfill the performance requirements for the design service life at a required probability level. Obviously we use limit state concepts, but on the graph here on the right hand side, the vertical axis is resistance and load effects, and on the horizontal axis that's time. And you can see the blue line is the resistance curve, which is shown deteriorating with time, and the red line is the load effect increasing with time. So that might be physical load, but it might also be environmental load. And as those two curves increasingly overlap with time, you end up with a basis for establishing service life. However, if we seek to take into account that there are other resistance effects which are not typically taken into account for design, such as compressive membrane action, which will give a larger structural resistance, we can use that as a basis for evaluating an extended service life for an existing structure. In these analyses, we will use a concept of levels of approximation, which relates to the sophistication of the analytical treatment employed. So in this graphic, you see accuracy on the vertical axis and time devoted to analysis on the horizontal. In this example, there are 4 levels of approximation defined. So the lowest one is the simplest safety format. So that might use, say, hand calculations or spreadsheet models, and the most sophisticated is probably going to be a non-linear finite element analysis based or possibly linked to other evaluations. So you see improved accuracy with higher levels of approximation, but obviously for lower levels of approximation, you're expecting a smaller analysis effort to be required. So I'll just seek to give an illustration of that and how we might consider load carrying behaviours not normally considered in design to justify a higher load capacity in existing concrete structure. So here we're using compressive membrane action and levels of approximation. So this picture shows a slab through a concrete section through a concrete bridge deck, where the slab is mobilizing a compressive arch action, and we can represent the punching shear capacity by using the rotation developed over the supports there, and this enables a relationship to be established between rotation and punching shear load. So here you can see that there are different forms of analysis: no PS, no pre-stress, and at the top we've got pre-stress with compressive membrane action and using an advanced levels of approximation methodology. So the higher load capacity has been justified by the improved accuracy of an advanced level of approximation method. There's a paper reference down there in the bottom right hand corner which describes this in more detail. In terms of existing structures, one of the things that we are needing to take into account is the deterioration processes and how to model those to understand the impact upon the structural performance of structure. We've divided these into initiation and propagation models for concrete as a material. So that may suffer from physical deterioration and damage processes, might be affected by chemical deterioration or biological deterioration processes. And there's still much debate on how far we can get in Model Code 2020 with these forms of deterioration and our representation of them in the code. And we recognize that there's probably too much development required for detailed models on many of these topics for them to be incorporated in Model Code 2020. If we turn attention to initiation propagation models for reinforcement corrosion, i.e. by carbonation-induced or chloride-induced corrosion, but possibly there are other corrosion mechanisms that we would need to take account of. Seeking to take this forward, last year there was a workshop in Paris on mathematical models for reinforcement corrosion. It led to quite strong debate on various aspects of how the modelling could be used, and we're still working on that, and we need to see how far we're going to get. But in terms of future aspirations, one of the things we'd like to be able to do is evaluate the implications of cracking upon durability more effectively. But also, you know, in the longer term, there must be the aspiration to undertake a durability assessment, a residual service life evaluation after interventions have been made. So long way further to go with many of these aspects. So they'll be treated in later updates of the code. Let me just mention a case history where it illustrates the role of monitoring and the value of information upon management of an existing structure. So the objectives of these areas of activity are to improve the quality and safety of constructed assets, potentially to extend their useful life, but also to provide diagnostics and assess in risk management, risk assessment for existing structures. And the goal eventually will be monitoring safety in real time. This shows some of the factors influencing the behavior of a structure: variation in the applied loads, loss of strength due to various factors, perhaps the impact of inadequate maintenance, but also the structure may be adversely affected by design errors or manufacturing defects or construction defects. And of course you have adverse impacts from, or positive impacts as well, from anthropic interventions. There's also natural events such as earthquakes and floods, which may lead to extreme events that perhaps low probability, high consequence events, whereby you need to make an evaluation of the structure in terms of whether it's lost some structural integrity and whether it's safe to remain in continued service. So in terms of an example, this deals with real-time monitoring. There are, this comes from a paper you'll see at the top there in the header, which describes the use of MEMS clinometers and MEMS accelerometers. So MEMS is a micro electromechanical system. And today I'm going to talk briefly about the tunnel monitoring case study. So two large tunnels were built, about 2 kilometers long, each housing a 3-lane motorway, but they had to be positioned through an unstable area of ground where there was the potential for landslip. The interiors of the tunnel walls were monitored by or instrumented by 762 MEMS clinometers, and I'll show you the layout of that. So there were sensors which were picking up on longitudinal movements and sensors which were picking up on changes in the transverse section at 9 locations. So the sorts of data which were received, on the left-hand side you can see deformation of a tunnel cross-section, and on the right-hand side you can see the longitudinal profile of the tunnel. So both deformations on the cross-section and undulations along the length. And obviously that provides displaced shapes, and you can understand the impact of that by using modeling to represent the behavior and the safety of the tunnel shell. So that information feeds back into life cycle monitoring through a system which will probably also bring in information from NDT inspections, lab testing, and the like to enable an assessment to be made of the existing safety of a structure, but also to make a prognosis about future circumstances. And finally, I'd just like to touch upon that Model Code 2020 will be dealing with interventions upon structures. And again, there's a supporting paper highlighted there as to thoughts on this, which have been developed somewhat since that paper was written. But we're relating back to, as we do where possible, other guidance. Here we're using the ISO 16311 suite of documents on maintenance and repair concrete structures. So we're approaching identification of problems in terms of defects in concrete, reinforcement, corrosion, and also where structural enhancement is required, and coming up with principles for interventions or management, associated with these. So we're looking at using this approach for 5 types of interventions: maintenance, preventative interventions, remedial, i.e. Improving the current condition of the structure, strengthening and upgrading, and then reconstruction or replacement. So to conclude the presentation, I'd just like to say that Model Code 2020 has a lot of innovations which are relevant to the design of new structures and the through life management of existing ones. And we have this strong focus upon sustainable design and life cycle management. But some specifics of the innovations and so on are grouped there for new structures, adapting of existing structures, and also the management of existing structures. So if you look at new structures, there's the ability to use new materials, new concretes. We're advancing models for durability and surface life design, considering structural behaviours not normally considered in design, as I illustrated in the talk. New information on dealing with actions on structures, fibre concrete monitoring, global structural behaviour and modelling, as well as life cycle management. In terms of existing structures, in addition to the above, we're looking at procedures for assessment, dealing with conservation requirements, clearly monitoring and life cycle management, but also performing remedial, upgrading and preventative nature interventions. So I'll leave it there.
One of the questions is from Vyacheslav Javakowski to Professor Matthews. What about the type of cement for the durable concrete with cement content less than 100 kilos per cubic meter?
A lot of that comes from particle packing, but it's certainly been demonstrated by various colleagues in FIB and in universities that you can, I think Jos Walraven demonstrated an effective concrete mix with only 70 kgs of cement, but many of these developments have been focused and achieved by dealing with and optimizing the particle packing arrangements rather than using the cement as a filler. But of course, one of the points which was being made is that there are restrictions in the current codes which prevent you reducing your cement content below maybe 300 kgs because that's what's deemed to be the minimum allowable. So we're hoping that we can move slowly in a positive direction to allow new developments, new processes to be taken up by industry, obviously and supported by academic work in the future.
Thank you. We have a second question by Roberto Torrent. In Model Code 2010, stem classes C12 and C16 exist. You mentioned C20 as the lower limit. Is it valid for structural concrete?
Depends on what type of situation you're in. But yes, C20 is quite low. But then if, let's say, we are using something which is quite a low strength, if we've got reinforced autoclaved aerated materials, their strength is quite low, but they are used successfully. So I wouldn't take the 20 too literally. It's still in a process of being resolved, and that area of work's being led by Harold Muller. Yeah. So we're awaiting their outcome as to what their recommendations are.
Fine, thank you very much. I have one comment more than a question from George Wardek. We know that it still lacks the models of requalification of materials as well as the existing structure. Is it possible to propose benchmark for sustainable concrete in terms of fracture properties?
I don't know. How are things moving on in the sustainability subgroup, David? Have you given any consideration to that in your?
Yeah, well, it's for qualification of materials, not for sustainable concrete. Yes, but not in terms of fracture properties.
Yeah, because what we're really looking for is sustainable structures, and perhaps a little bit less emphasis on sustainable or low impact materials.
Yeah.
Yeah, because you can have a low impact material and still have a high impact structure. Yeah. If you use, because there's views that we use 50% of the concrete materials that we use are wasted. You know, you could remove 50% of the concrete.
And I think now we don't know a lot of things that we'll have to test, and this is the
yeah. So hopefully we're opening a way forward where we can make progress towards. I wouldn't claim that we've got all the answers to all of the things. No. We're just trying to provide ways forward where people can make innovations and help progress to the type of future that's seen, you know, low carbon, with perhaps less barriers to the uptake of technological progress.
I have a last question from Mohan Kalgal. It says, in India, there is a strong reservation on using triple blended cement for structural concrete. Your views?
Well, they seem to work fairly well from,
yes.
from my understanding. I don't know, do we have another material specialist? I'm not a material specialist as such. Quaternary blends I thought were coming in as the thing to go for.
Yeah, we can say that the model code is dealing these aspects and will give some recommendations on how to use this, but we don't have the rules today, but possibly when the model code is finished, we'll have some rules or some recommendation on how to test these materials.
Yeah, so we're working on that at the moment. We've yet to see the final proposals, but it looks very interesting and very promising. And hopefully we'll see more detail in some of the meetings over the next months.
Yes. Okay, thank you very much, Stuart, for your presentation and for the answer of so many interesting questions that I am sure that we have more in the future. And we have to go a little bit to the next speaker.
Yeah, just remind people there's a lot of hidden information which I wasn't able to present today.
Yes.
All right, thanks.
Thank you very much.